Well, it's a pleasure to be at this first Clay conference. I'd like to talk today about some new and yet very basic examples of dynamical systems of algebraic origin. They're quite rigid, and they arise by various processes that start with an algebraic number and somehow end up with a geometric object with an automorphism. And it's a pleasure to give this talk after the other topics that have been brought up so far, because it will touch in, however incidental or superficial way, on, for example, knots and rational points and minimal models and equidistribution and the persistence of mathematical culture. Okay, so let me begin, but just in a superficial way each. Okay, so let me begin with a number theory question. What is the smallest integer, lambda, greater than 1? Now, to clarify why the answer to this is not known, by integer, I mean algebraic integer. So a root of a monic polynomial with integral coefficients. And of course, such a polynomial has many roots. And by smallest, I mean the following. You look at all of the roots of the minimal polynomial of this integer. And some are inside the unit circle, some are outside. You take the product of the ones outside, or their absolute values, and that's a measure of the size of this number. And the question is, what's the smallest that you can make this product? Of course, you can make it 1, for example, by taking a root of unity. But what's the smallest it can be, assuming that this product is bigger than 1? So that's the question. The conjectural answer is known. And I should say I'm going to try to focus as much on open questions and examples as I do on theorems in this talk. So here's an open question, or here's the purported answer. So here's a very special kind of algebraic integer. Almost all of its conjugates are on the circle. This one has degree 10. There's 2 conjugates that are off the circle, one inside and one outside. And so in this case, the Mahler measure is just this conjugate lambda, which is greater than 1. This is what's called a Salem number. And well, here's its size, 1.17 something rather. Here's the polynomial that it satisfies. And this polynomial was discovered by Lemers in one of the first computer searches ever carried out in mathematics in the 1930s. And it's conjectured to be the smallest algebraic integer in this sense. The conjecture is known up to degree about 40, but certainly not for infinitely many integers. Now, what is Lemers' number? Why did he have to use a computer to find it? Why wasn't it already known? Well, these days, we know that Lemers' number has several mathematical manifestations. One of them is it occurs as the Alexander polynomial of a certain Pretzel knot. So a Pretzel knot is, well, this is an example of a Pretzel knot. This one has 3 numbers attached to it, and the 3 numbers, the integers, tell you how many times to twist in each of these vertical lines here. So you can add more vertical pretzels, and you can make each pretzel itself longer or reverse the direction of the twist. So this is called the -237 Pretzel knot. And it's a remarkable fact, which was just noticed as a kind of empirical fact, that among if you start looking through knot tables, you see Lemers' polynomial coming up. And there's something very suggestive here about the fact that 2, 3, and 7 is also the signature of the smallest volume triangle group. So in fact, there are many manifestations of Lemers' number geometrically. This is just one. But what I want to focus on today is another geometric manifestation, which is in the theory of Coxster groups. Now, what is a Coxster group? Well, it's a group acting by reflections on Rn with respect to some inner product. And the group can be succinctly described by a diagram. So I'm showing you the particular case of what's called the E10 diagram here. And the way it works is your vector space has a basis element for each node in the diagram. And then the inner products between elements are typically 0. But if they happen to be joined by an edge, you make the inner product -1, and you make the length, or the squared length of each element equal to 2. So this is just a shorthand for a sparse matrix that describes a quadratic form. And in fact, this is an integral quadratic form, since these inner products are all whole numbers. And the group generated by reflections in each of these vectors with respect to this quadratic form is called the Coxster group or the Weil group associated to this diagram. And it preserves the integral lattice generated by these vectors as well. So, for example, if you look at the characteristic polynomial of one of these gadgets, that will be a monic polynomial with integer coefficients. And so the eigenvalues of these Coxster, the elements of this Coxster group, are examples of algebraic integers. Now, it's a well-known philosophy in the theory of Coxster groups that in this big group, there's sort of one important element or conjugacy class to be discussed that carries a lot of information about this diagram and the group as a whole. That's called the Coxster element. And it just means you take the reflections through the vectors corresponding to each of these nodes. So I let SI denote reflection through the ith, in the plane perpendicular to the ith vector, and you just take the product of those in any order. I happen to put them down 1 up to 10, but in this case, and whenever the graph is a tree, if you reorder the elements, you get something conjugate to what you started with. So like the Frobenius, this Coxster element is really a conjugacy class in this reflection group. And this conjugacy class has a very simple meaning geometrically. So here's a slightly different example of a Coxster group. I just drew it because it's in low enough dimensions that you can see what's going on. This is a group that generates a tiling of the hyperbolic disk by reflections through the 3 sides of this triangle here. And so those reflections are the generators of the group. But you can think of an element in this group, rather than being a product of reflections, as you can think of it as really just a billiard path that's bouncing off the sides of this polygon. And every time you hit a side, you just apply the corresponding reflection in the group. And so this billiard path that touches each side exactly once is the Coxster element. And of course, we could go around in different directions and start at different points, but it would be it's well-defined up to conjugacy. And it turns out that among all the billiard paths that touch all the sides, this is the shortest billiard path. So that's one of the important features of the Coxster element. It samples all of the sides, but also it tends to be the minimal or shortest geodesic in this reflection group. OK, so here is another manifestation of Lemers' polynomial. It turns out that Lemers' number is the leading eigenvalue for the Coxster element in the reflection group E10. OK, now a couple of remarks are in order here. There's lots of Coxster groups that you may have heard of or be familiar with. There's the spherical and affine Coxster groups, which fall into series like AN, DN, E6, E7, and E8. But those all preserve a definite inner product on the space. And so the spectral radius of every element the group is finite. The eigenvalues are roots of unity. The spectral radius of any element is 1. So they're not going to give interesting examples apropos this question of small algebraic integers. But when you go to more complicated diagrams, when you go past E8 and E9, for example, and get up to E10, then it turns out the corresponding inner product space is hyperbolic. It has signature 1n. And the Coxster element becomes a translation along a hyperbolic geodesic. And the log of the Lemers number is the length of that geodesic. And this connection between Coxster elements and lengths and Lemers number and so on was exploited by Echo Hironaka to prove that among Pretzel knots, among the Alexander polynomials of Pretzel knots, Lemers' conjecture is true. That is, if Pretzel knots are the only way you can think of making up algebraic integers, then in fact you have seen the minimal one already with Lemers' number. And the proof was to relate the Alexander polynomial for Pretzel knots to the Coxster element for certain graphs, namely the graphs which are stars. Well, when I was just learning about Coxster groups in a seminar with Dick Gross and Dan Alcock, and so I studied Echo's work, and I eventually proved the following theorem, that in fact, the spectral radius of any element in any Coxster group is either 1 or it's bigger than Lemers' number. And that the spectral radius is certainly a lower bound for the Mahler measure. So again, every element in every Coxster group satisfies this conjectural lower bound, and the Lemers number itself is realized geometrically by this E10 diagram. And let me just give you a hint of the proof. So it's nice, there's a sort of monotonicity theory for these Coxster diagrams. As you start adding more vertices or edges, the diagrams become more and more nearly hyperbolic. They start out spherical, then they become affine, then they become hyperbolic, maybe signature PQ even, where P and Q are both positive. So after the spherical and affine groups, there's a sort of next layer of Coxster diagrams, which are the minimal hyperbolic ones. And there's 38 of those. And the eigenvalues of their Coxster elements and their characteristic polynomials and so on, the diagrams themselves are summarized here. And here's our friend E10 entering. And it just happens that the proof is by a verification experimentally that among these minimal diagrams, Lemers' number represents the smallest value for the spectral radius of the Coxster element. And then there's a monotonicity argument that says that these things in turn give a lower bound for all elements in all Coxster groups. OK, so that's my algebraic preliminary. Now I'd like to turn to another question, which is maybe not quite as well posed, but moves us in the direction of dynamics. So the theory of dynamical systems goes back to at least to Poincaré, who developed them in the setting of celestial mechanics, or if you like, in the setting of classical Newtonian mechanics, to study things like the three-body problem, to study differential equations where it was impossible to solve the differential equation exactly, but where one could nevertheless try to develop some qualitative understanding of what happens under time evolution. One of the great things about celestial mechanics is that there is a measure on the configuration space of the solar system, for example, that is preserved under time evolution. And so using this invariant measure, Poincaré would prove, for example, his recurrence theorem that says if we wait long enough, whatever's happening today will happen almost exactly the same thing far in the future with probability 1. OK, so this is the classical origin of dynamics, having to do with differential equations. But Poincaré also reduced a technique for discretizing this evolution. Namely, you take a cross-section to the flow describing your dynamical system, and then you just wait until you come back to that cross-section again. And so instead of having to analyze a long, long trajectory, much of which you don't really care about because you know all the trajectories will go in the flow direction, you analyze the first return map to this cross-section. And there the trajectories are represented by single points. And your continuous time parameters were replaced by a discrete one. So in the era of Smale and Anosov, there emerged a beautiful theory of dynamical systems in the following more mathematical setting. A dynamical system should live on a compact manifold, and it should be given by a diffeomorphism of this manifold to itself. This is sort of an abstraction of the idea of the Poincaré cross-section. Now, what I'd like to do is to make this theory even more rigid. I would like to study the case where the compact manifold is, in fact, a complex manifold, and where the map F is holomorphic. And the reason is that there seems to be, in general, more hope of getting a complete picture of what's going on with the dynamical system when it's, say, is holomorphic rather than just smooth. And maybe this holomorphic system will really be the complexification of our original system. There's a well-known tradition in algebraic geometry of taking classical problems and first trying to solve them over the complex numbers where Bezout's theorem will hold correctly, for example, where the number of roots of a polynomial will be equal to its degree. So given that we've confined ourselves to this rather rigid setting, this mathematical idealization, we can ask, what is the simplest, interesting dynamical system? We'll see. So here's the first example one might look at. I seem to have lost some of this figure here. It's visible on my screen, but not on yours. OK, so I'll explain that. So here's one example. I mean, a further virtue of looking at this setting is maybe, in fact, X is an algebraic variety, and the map F is even defined over Q, and maybe the orbits will be rational points, and they'll tell us something about the distribution of rational points as well. Or maybe at least the map is given by a formula, and so we can simulate it very easily on the computer. So the example that I've drawn here is, which I call the Bowtie examples. These are obtained by, from an algebraic curve that's really should be thought of as sitting in P1 cross P1, product of two projective lines. It's given by an equation in x and y that has degree 2 in each variable individually. And so if you start with a point and you draw the vertical line through that point, it meets the curve in exactly one other point. But then you can play this ping pong game where you now draw a horizontal line and see where that meets the curve. Well, this way. You draw a horizontal line and see where that meets the curve, and then you draw a vertical line again, and so on. And you just keep bouncing back and forth in parallel to the two coordinate axes. That gives you a dynamical system on this algebraic curve. Now, sometimes there are periodic trajectories. And the amazing fact is that if there is one periodic trajectory, then all of the trajectories are periodic. As soon as this orbit closes up, it closes up independent of where I start on this bow tie. That's rather atypical, though. If I perturb this bow tie imperceptibly, then that orbit blows up into this one, which is in fact dense on the curve. I have only drawn a very large portion of it. So this periodic behavior is very unstable, but once it's achieved throughout the bow tie. Okay, now why is this true? This amazing fact that once one orbit is periodic, they all are. Well, it's very simple. What is the genus of this curve? The genus of this curve turns out to be 1. That is, it's an elliptic curve. Now, what does it mean that the genus is 1? It means that there's a one-dimensional space of holomorphic 1 forms on this curve. But these holomorphic 1 forms, which are locally just something like f of xy dx, say, on the curve, well, when you restrict them to the real locus of the curve, they give you a metric on the curve, because you integrate the 1 form and call that the length of an interval. And so because of the fact that the space of 1 forms is one-dimensional, this metric is preserved by all automorphisms of the curve. And so this map, this induced map of the bow tie to itself is in fact an isometry of an abstract circle with respect to the metric determined by this 1 form. So it's just a rotation. The rotation of a circle can either be rational or irrational, and that's the end of the story. This is not interesting. It's not interesting because all of the orbits behave in the same way. And there's only the mildest kind of chaotic phenomenon, like what you see here. But even more to the point, if you start with 2 points that are close together, then they remain close together for all time. So there's no instability in the dynamics. And I should mention that this bow tie picture is closely related to Poncelet's theorem, which has to do with what happens when you try to inscribe and circumscribe around in between two conics in the plane. If you can circumscribe in/circumscribe an n-gon starting with 1 point, then you can do it for any point. That's the same phenomenon. Well, shall we try some other genera? What about genus 0? Well, for genus 0, our curve is just the projective line, and any map to itself will be essentially a linear map. Also uninteresting. So genus 0 is not interesting. And what about genus 2 or more? Well, now the automorphism group of our curve is finite. We're in the realm of general type in the much more general setting that Maury discussed. And so, again, there's no interesting dynamics. The orbits are all just simply finite sets. So the conclusion is there are no interesting dynamical systems in complex dimension 1. And now perhaps by induction we can prove there are none at all. So let's go to the next case. Surfaces. So surfaces have a classification quite similar in some ways to the classification of Riemann surfaces. Namely, there are rational surfaces, which are surfaces that are essentially P2. They're birationally equivalent to the projective plane. And then there are highly irrational surfaces, which are those of general type. But those only have a finite automorphism group. And so they can be dispensed with. And then, again, there's something like the genus 1 case. There are surfaces that you get by taking the quotient of the complex 2 space by a lattice, just the higher dimensional generalizations of a complex torus. And their automorphisms are also essentially linear. They come from automorphisms of C2 as a linear space. And so they're not interesting. So we've almost proved dimension 2 is also not interesting. However, in dimension 2, there's a totally new kind of object that you don't see among one-dimensional varieties. It's called a K3 surface. So a K3 surface is a surface is a compact complex surface with the following two characteristic properties. The first is that the canonical bundle is trivial. Now, what this means in down-to-earth terms is there exists on the surface a holomorphic 2 form that is sort of a holomorphic version of an area element on the surface, which is nowhere 0. And it's easy to see this form is unique up to scale. It's a section that trivializes the canonical bundle of the surface. Now, when you take C2, C2 also has an obvious holomorphic 2-0 form on it, which is invariant under the action of the lattice. So like the complex torus, the K3 surface has a trivial canonical bundle. But unlike the complex torus, the fundamental group of the K3 surface is trivial. So it's a new kind of object. And it turns out that these objects can have rather rich automorphisms. Now, how can I give you a concrete example of a K3 surface? Well, I learned from Barry Mazur how to do this. You just generalize this picture to one dimension higher. That is, in the product of 3 P1s, you take a surface which has the property that it meets every vertical, horizontal, or depth-wise line in exactly 2 points. So we just generalize this to one dimension higher. And let me look at show you a picture. So this is supposed to be a picture of such a surface. There's an algebraic equation that defines it. You'll notice that this equation is of degree 6, but in each variable individually, it's of degree 2. And what that means is that each line parallel to one of the coordinate axes meets this surface in 2 points. And so we can again define a ping-pong style iteration. We start with a point, and then we just change its x-coordinate, keeping the y and z coordinates fixed. There's a unique second point on the surface that lies on the same horizontal line. And then you so in other words, this surface has 3 involutions on it, defined by the 3 coordinate axes. Just take their product. That turns out to be an interesting automorphism of this surface.
What do you call that, a ping-pong iteration?
I don't know. I'm open to new suggestions. Sorry? Okay, so let's see. Where was I? Oh, yeah. Now, remember that like the torus, like the case of this curve of genus 1, there's an invariant 2-0 form on the surface. And that really pinned down the dynamics on this elliptic curve. It kept it from being interesting. what's the analogous phenomena for this algebraic surface? Well, what happens is we get an invariant area measure on the surface from this 2 form. When we restrict this to the real points of the surface, or take its absolute value, this determines a measure on the surface which is invariant under any automorphism. So this automorphism is measure preserving. And this makes it more interesting rather than less. This makes it much closer to the automorphisms of celestial mechanics, which also preserve, like any Hamiltonian dynamical system, a symplectic form, and therefore a volume form on the phase space. Question?
When you take its absolute value, what sort of metric are you thinking about?
It's not a metric, it's a measure. So the absolute value just means that you integrate this function times dz1, dz2 over some subset of the real points on the surface. Okay? I mean, in the same way that the absolute value of dz on a Riemann surface determines a line element, the absolute value of a holomorphic 2-0 form determines an area element on the real points. So in any case, this automorphism turns out to be area preserving. And what I've drawn in this picture is, well, I've rendered some typical long orbits, just chosen at random, as seen from the top. So you look down at the top, and if you pick a point sitting over here on the surface, then under iteration, it runs along this densely on this invariant curve. And in fact, it looks like almost the entire surface is organized into these invariant islands. On the other hand, the rotation numbers vary quite a bit as you go from one circle to another, and there's also these strange gaps, and there's something funny going on here. So anyway, that's what you see for one parameter value. Let's increase the value of this parameter here to 2.5. So the surface is almost unchanged, but the dynamical system, it looks much qualitatively much richer. In addition to seeing these big periodic islands are starting to decay, and they're surrounded by smaller islands of higher period. But emerging between all of them is what looks like a so-called stochastic sea. That is, it looks like there are also orbits that fill out a set of positive measure that aren't trapped in any way and maybe have highly aperiodic behavior. They certainly don't look like they move along invariant circles as they do in these elliptic islands. And if we increase the parameter quite a bit, make it more like a three-dimensional bow tie, well then, here I've drawn the picture of one orbit. It appears that in this example, every orbit is dense. Although I have to say, experimentally, it would be extremely difficult to tell whether or not there's an extremely small elliptic island somewhere of enormously high period, or whether or not, in fact, this is, say, an ergodic dynamical system. I mean almost every orbit dense. Yeah. Now, let's return to the tamest of these, this picture here. And what I'm going to do is blow up a little part near the center. And what you see is that even in this very tame picture, where most of the surface is filled by these elliptic islands, there is, on a small scale, something that looks just like this stochastic sea. And in fact, apart from this picture where it looks like there's a dense orbit, all the pictures look like one another. So let me not put that into words myself, but read you something from McKay's book on area-preserving maps, 1993. He says, "A few hours playing at a computer terminal is sufficient to convince one that almost all area-preserving maps have essentially the same features. First, one sees stable periodic orbits. So those are things that are, say, confined to the centers of these disks. They're trapped there. Their stability comes from being surrounded by closed invariant curves." That's what we've just been discussing, these elliptic islands. Secondly, in between some of the larger invariant circles are island chains, strings of alternating stable and unstable periodic orbits. That's these islands that are circling other islands that we see. And thirdly, when they are large enough, one can see they are surrounded by a sea of stochastic orbits. these orbits are repeated on smaller and smaller scales. And so, in summary, there seems to be only one picture. And how do these pictures fit together? Suppose we vary this parameter a continuously. Well, here's a movie showing what happens, how you make the transition from the very periodic behavior where almost everything looks like an island. There. Then we start to see a stochastic C growing, and the elliptic islands seem to be winking away and maybe completely disappearing. So if you look at these individual pictures for a long time, and you look at the movie for a long time, it's quite easy to write down, say 10 conjectures or so, none of which can have been resolved. For example, you might conjecture that in this picture, the elliptic islands are dense, but also the stochastic C has positive measure. You might conjecture that when you move around in parameter space, maybe there's an open dense set of points where you have some elliptic islands, and maybe there's a set of positive measure, like here, where the islands disappear completely. Those are the first two of, say, 10 obvious conjectures which have been addressed from a very technical point of view in many interesting examples. There's something called the standard family, and yet no resolution of these conjectures has really been obtained in any of these specific examples, despite the robustness of the phenomenon. Well, so why don't we investigate what happens if we work over the complex numbers rather than the real numbers? So what would happen if we took one of these examples that has an elliptic island, like this one, and I mean, after all, it's defined by algebraic equations, so we can iterate just as well over the complex numbers as the reals. Let's make the points very slightly complex and take its orbit and project it to the real plane. Well, this is what you see. So this is the example with huge invariant islands. I've just taken a typical complex point, even starting close to one of those islands. And as you can see, well, I can't tell whether or not it's really dense on the four real dimensional surface, but certainly its projection to the plane looks dense. Not only that, but the projection to the plane favors some regions in the plane more than others. What is the asymptotic distribution of this set of projections? Well, there is an invariant measure on the complex surface. Namely, you can take this 2 form and wedge it with its complex conjugate. That gives an invariant measure on the 4-dimensional space. And this shading here is just the push forward of that measure to the plane. So this is our Sato-Tate measure for this particular dynamical system. It looks like the real projections of points are uniformly distributed with respect to this measure. So again, this I thought, when I first began investigating this, I thought this is seems to be a very robust phenomena, but I've never been able to prove it. I've never been able to prove that there is a single example of this ilk that has elliptic islands over the reals, but has a dense orbit over the complex numbers. Out of frustration, I decided to try to go the other way and try to prove that there's some examples over the complex numbers where the orbit is not dense. Maybe there are elliptic islands in the complex realm. Well, it turns out, in fact, there are. And this is one of the few theorems I'll present. There exists a K3 surface and an automorphism which has a complex invariant island. This is called a Zegal disk. It just means there's a domain on the surface in the 4-dimensional manifold. And there's an open set which is mapped to itself. And in fact, it's mapped to itself by a map which is conjugate to a rigid rotation, holomorphically conjugate to a rigid rotation. Now, how would we ever prove that such an island exists? Well, it turns out that the existence of such an island can be deduced from Hodge theory. That is, if you just look at this automorphism acting on the middle dimensional cohomology of this space, and you know the Hodge decomposition of that space, well, first, you can, as a topologist, you can figure out how many fixed points the map has using the Lefschetz formula. That turns out to require that the trace of this endomorphism be -1. And then a more sophisticated fixed point formula of a T and bot lets you determine the derivative at that unique fixed point, or at least its eigenvalues. And if that's consistent with being a rotation, it might be that, in fact, the map is conjugate to a rotation near that fixed point. And in fact, their suitable results from transcendence theory ensure you that this map is not close to being a periodic rotation. And then a work of Zegal, generalized by Sternberg, shows that, in fact, the map can be linearized near that point. That is, you can change coordinates so it becomes a rigid irrational rotation of a two-complex dimensional space. So that's the analysis part. If I could only find a map of a K3 surface to itself with these properties, then I would have my Zegal disk. Now, how am I going to find a K3 surface with those properties? Well, this is the synthesis part. We just start out not with the K3 surface, but with the characteristic polynomial we would like for its action on the middle dimensional cohomology, which turns out to be a 22-dimensional space. So I write down a polynomial of degree 22, and then I hope that I can find a K3 surface and an automorphism that realizes that characteristic polynomial. How could that possibly be true? Well, first, Dick Gross and I proved that given this small amount of algebraic information, you can lift it a little bit. That is, you can actually find an endomorphism of a 22-dimensional lattice that preserves an inner product of the right type, an even unimodular inner product of signature 319, which happens to be the same as the cohomology of a K3 surface with its intersection form. And furthermore, one can then find an invariant Hodge structure on this lattice. And then the Torelli theorem for K3 surfaces ensures you that there is, in fact, a K3 surface. With that Hodge structure, it's essentially unique. And therefore, this automorphism induces an automorphism of the K3 surface. So in other words, to find this Zegal disk, I just needed to find this characteristic polynomial with the right assumptions to allow the rest of the process to go through. And it turns out that if you look at this, because of the signature here, and also the way the form being definite on the space of two forms, that this polynomial will in fact be a Salem polynomial. That is, it will have all of its roots but one on the unit circle. And what makes this process difficult, what makes it hard to find, is the fact that to apply the Lefschetz formula, that Salem polynomial has to have trace -1. Now you'll remember that a Salem number is this positive real number, and all the rest of its conjugates are on the circle, and its trace is the sum of this positive number, bigger than 1, plus all the conjugates. So that means the conjugates have to be sort of crowded into the negative half plane so that the trace can come out to be negative. And so it turns out that among, for example, the 630 degree 22 Salem numbers that you can get by making all of these coefficients 0, 1, or -1, there's 630 of those, 596 have trace 1, 33 have trace 0, and 1 has trace -1. So we eventually found some examples that work, maybe 50 or so, but in fact there are only finitely many examples of Salem numbers with this key property. Nevertheless, there was at least one, and so that shows there do exist K3 surfaces with these beautiful complex invariant islands on them. That it's not, that the dynamics can be quite rich in the sense that some orbits will be trapped, and potentially there's plenty of other orbits that have much more chaotic behavior. Now, the next slide should be a picture of this island, right? Well, it's something I forgot to tell you. In the theory of K3 surfaces, there are, I didn't ever say really that K3 has to be an algebraic variety. In fact, most K3 surfaces are not projective varieties. And it turns out that this surface is not projective. And in fact, you cannot make a projective K3 surface with a Zegal disk on it. So these things exist, but they exist not quite in the world of algebraic geometry, but more in the world of transcendental algebraic geometry. And unfortunately, I don't have a concrete dynamical system that I can simulate on the computer. So that's where matters stood for some time, and I began to wonder if maybe one could formulate some conjecture that maybe all dynamics is chaos on algebraic projective surfaces, because I couldn't make these Zegal disks live in that setting. And I formulated such a conjecture at Lumini a few years ago, and immediately afterwards I learned from Eric Bedford that this conjecture is not true. And how is it possible that there are some additional examples when these K3 surfaces are so constrained? Well, Eric said, I have some examples that have rich dynamics, what's called positive entropy, and they also have attracting bases. There's some points that, such that under iteration, a whole open set tends towards this point. So there's stable orbits which converge there, and maybe a lot of unstable orbits which don't. Now, that doesn't look right to me, because in my examples, there's an invariant area form. All K3 surface automorphisms have an invariant area form, so they can't have attracting or repelling fixed points. They can only have sort of indifferent fixed points. So where's this example coming from? Well, it turns out that if you're in my algebraic geometry education, I was learned to treat rational surfaces sort of dismissively. I thought a rational surface is basically P2, and so end of story. It turns out these examples live on rational surfaces. And the theory of automorphisms of rational surfaces is exceedingly rich. So I want to conclude by describing some new examples of automorphisms of rational surfaces. That is, surfaces which are obtained by just blowing up the projective plane at n points. And just to say a word about the theory of minimal models, in the theory of surfaces, the reason rational surfaces are special is that they don't have a canonical minimal model. You can go up and down, and they can dominate various, in a birational equivalence class, you can dominate various different minimal models. There's no canonical minimum. But perhaps the right object to consider is not the rational surface itself, but the rational surface plus an automorphism of the surface, or plus an action of a group on a surface. And if you take the pair consisting of the surface plus this dynamic, then, in fact, there often are canonical minimal models. And this point of view was emphasized by Manin, who treated on an equal footing the complex automorphisms of the surface, as well as the action of Galois groups on surfaces defined over number fields. So the lesson is there's a lot more to rational surfaces than you might think. Just because they're equivalent to P2 doesn't mean the dynamics of an automorphism of the surface descends to P2. So let me tell you what's known about automorphisms of rational surfaces. They turn out to be closely connected to Coxster groups. Namely, if you take the projective plane and you blow up n points, what happens to the cohomology? You have an initial z coming from the hyperplane in the original P2, and then when you blow up points, you start out with the plane P2. This has a hyperplane in it, H, with self-intersection number +1. And then you blow up some points. These become exceptional curves on the blow up, and these have self-intersection number -1. So the intersection form is very simple. It has a +1 and then a bunch of -1s coming from the number of points you blew up. So H2, together with its intersection form, is what's sometimes called Z1n. It's the Minkowski lattice, the standard inner product on an n+1 dimensional free abelian group. Now, of great importance as we learned earlier, in the theory of algebraic varieties, is the canonical bundle. And within H2, there's the canonical class. The canonical class on P2 is -3 times the hyperplane. And on this blow up, it turns out to be just -3, 1, 1, 1. And any automorphism is going to have to preserve that canonical class. And so it will have to preserve its perp within this, this lattice with respect to the intersection form, and its perp turned out to be exactly the En lattice. That is the lattice described by the En diagram, which we saw earlier in the world of Coxster groups. And then, so of course this lattice has to be preserved, but among the automorphisms of this lattice, there's a special subgroup, namely those generated by reflections in these roots, these elements of the particular basis chosen. And a theorem of Nagata says that, in fact, every automorphism of X lies in the Weil group, or the Coxster group, corresponding to this En diagram. So it's a subgroup of OZ1N. It preserves the intersection form. But moreover, it has to be an element that's generated by taking products of these reflections. OK, now, of course, when you start out with small, so let me tell you the theorem. So I'll say an element of this Weil group, which is an abstract group, is realized by a surface automorphism if you can find a particular configuration of endpoints to blow up so that that element then acts by an automorphism on the cohomology of the surface. And here's the theorem. The Coxster element can always be realized by an automorphism of the blow-up of P2 at n special points. Now, remember that in the theory of Coxster groups, we start out in the spherical diagrams, and then we gradually move in this more and more hyperbolic direction. For the spherical diagrams, the Coxster element has finite order. And here's an example. If we look at the Weil group W3, which turns out to just be the symmetric group on 3 letters, the Coxster element turns out to have order 6. And, symmetric group on, let's see. Let's look at the automorphism. So here's the automorphism an automorphism associated to the blow-up of the projective plane at 3 points. So we have we take the pair xy in the ordinary projective plane, and we map it birationally to y over x. Now, what does that automorphism do? It turns out that it blows this point here up to a line. It blows that line down to a point. It blows that point up to a line. It blows that line back down to a point. And it blows this point up to a line, that line back down to the original point. And you'll notice, if you iterate this automorphism, that after six steps, you come back to where you started. So it's a birational automorphism of the plane, which has the property that after 6 iterates, it gives you the identity. It's an element of order 6 in the Cremona group of the plane. Now, how do you make this into an honest automorphism of a surface that doesn't have any blowing up and blowing down? You simply blow up these 3 points here. And then you get a surface where this configuration of 3 lines becomes a hexagonal configuration. And then the automorphism is just a rotation of that configuration. So this is the first example of this realization theorem. And indeed, these special subgroups of finite order within the Cremona group were studied very classically. But people were interested in the finite order ones, and so they stopped when they got to E8. But what happens if you boldly continue to E9 and even to E10? Well, when you get to E10, you will find Lemers automorphism. This is an automorphism of the blow-up of the projective plane at 10 special points. And it acts on the cohomology with characteristic polynomial equal to Lemers polynomial. And this is an automorphism of infinite order. It turns out to have positive entropy, which means the dynamics is rather chaotic. And the entropy is measured by the log of the leading eigenvalue of the action on cohomology, which is simply the log of Lemers number. OK, now because of Nagata's theorem, every automorphism of a rational surface is built roughly in this way. It comes from an element of the Weil group, or the Coxster group, corresponding to some diagram. And we've seen that Lemers number is, so to speak, the smallest integer that arises in that way. And consequently, we have the following theorem. This map, F10, obtained by blowing up 10 points on the plane, has the smallest entropy among all surface automorphisms with positive entropy. So this is my candidate, finally, for the simplest interesting dynamical system. And here's a theorem that makes that precise, namely, this dynamical system has, in fact, the smallest entropy among all surface automorphisms, assuming you have positive entropy to rule out, say, periodic things and things like the identity. So let me finish by just showing you a little bit about how this gadget works. How do you construct this very special blow-up? Well, in fact, this map was first found numerically by Bedford and Kim. And for some reason, I thought it would be interesting to check if the 10 points they blow up lie on a cubic curve in the plane. There's a 9-dimensional space of cubic curves, so they shouldn't, but they did. But I was even more astonished when I drew that cubic curve and found out that it was a cuspidal cubic, which is what's drawn here. So in fact, this automorphism is obtained by blowing up 10 specially chosen points on a cuspidal cubic. And by the way, it covers a birational automorphism, which is only a mild modification of the formula I gave you before. You just put a plus a b here after this birational map. So this birational automorphism becomes an infinite order, quite interesting automorphism of this blow up of the projective plane. And to give you some idea of its dynamics, I've drawn here what happens to most points under iteration. Namely, almost every point under iteration converges to the cusp of this cuspidal cubic. And the remaining points that don't converge there form this rather exotic set of measure 0, whose real trace is being drawn here. This is the Julia set of this map, and this is where all the entropy and the periodic points reside. And it's quite remarkable that one can say here what happens to almost every point. There are very few algebraic dynamical systems in 2 or more dimensions where we can say what the behavior is globally of the dynamical system. But here, in fact, one can prove that everything converges, with an exceptional set of measure 0, to this cusp because of the fact that there is an invariant volume element again. What happens is this cubic curve, by virtue of being a canonical or anti-canonical curve on P2, gives rise to an invariant volume form of infinite measure on the surface. And that volume form is expanded by the dynamics. So we have expanding volume. And where is all the volume going to go? Well, the complement of that curve upstairs is non-compact, and points are just pushed towards that curve. And then on the curve, they're pushed towards the cusp. That's how an analysis of the global dynamics is possible. How are the points constructed? Well, once you see how to do the construction, it's almost painfully obvious. Let me say a word about why it's hard. I want to mimic the construction in the case of K3 surfaces. So for K3 surfaces, I said, OK, here's how I want the map to act on the cohomology. Now let's build the unique surface with such and such a structure. There is no Hodge theory on these blow-ups of P2. All of the Hodge structure, all of the classes are classes of type 1,1. So there's no Torelli theorem. There's no way to sort of see the different complex moduli of these surfaces. But if you restrict yourself to surfaces that are blow-ups of endpoints along a cuspidal cubic, it turns out that those do behave very much like K3 surfaces. And then what you look for is a solution to this commutative diagram here. If you have an automorphism that preserves the cubic curve, it will give you an eigenvector for the action of the Coxster element on the Picard group of X, which is just this EN lattice. And so you simply look you take one of the eigenvectors of this Coxster element, and you just use those numbers to figure out where the point should be on this cubic curve. So it can be, the positions of the points, which are rigid, can be read off simply from the entries in an eigenvector for the Coxster element. OK, so a few more examples. There's 2 other cases. What made that work, I should say, what was crucial, is that the Picard group, Picnod of a cuspidal cubic, the Jacobian of a cuspidal cubic, is not a complex torus. It's the complex plane. And what's good about that is that this group admits automorphisms, such as multiplication by lambda, where lambda is not in the circle. Its automorphism group is much richer than that of say, the Jacobian of a smooth cubic. And there's two other kinds of plane curves where the Picard group is C. There's the case of 3 lines through a point. So I've blown up 12 points on that configuration here to get a dynamical system. And there's the case of a conic, which is tangent to a line. That gives examples as well. Now finally, in these examples, I've been drawing a picture over the reals. And to get a picture over the reals, I had to choose one of the real conjugates of this, of Lemers number, or of one of these Salem numbers. So there was this number lambda here. It also had an inverse inside the circle. But there were also lots of other eigenvalues on the circle. What happens if I construct my automorphism using one of the corresponding eigenvectors for something on the circle? Well, then it turns out that you get a volume-preserving transformation, and this volume-preserving transformation always has a Zegal disk. It always has a complex invariant island. So I finally have an example of an automorphism of a projective surface, which has a Zegal disk. And here, oops, that's another example. Here's a picture of that Zegal disk, or rather the projection of an orbit. So if you have an irrational rotation of C2, and you take a typical point, that point will move around densely on a torus corresponding to the 2 eigendirections of the rotation, and its projection to the real plane will be the projection of a torus. So this is an immersion. What you're seeing here is an immersion of a 2-dimensional torus into the plane, and it's the real trace of an orbit of this dynamical system. OK, so these are quite rigid examples, but they exhibit a lot of interesting phenomena. And in some sense, they're made as simply as possible. That is, by using the first Coxster diagrams that have elements of infinite order, and by using blow-ups of the projective plane at endpoints. And I want to conclude by just saying, I think this illustrates an example of the persistence of mathematical culture. So there's a book by Cantor, written in 1895, which discusses the groups E6, E7, and E8, the corresponding Coxster groups, the corresponding Weil, and all of the Weil groups, in fact. And Weil was 10 years old. And Coxster wasn't going to be born for another 20 or 30 years. And then there was a sort of resurgence of activity in the work of Cobble in the 1930s. And what Cobble examined, he was sort of the first person to go beyond. Well, there should be many more loops here. He was the first person to go beyond the finite Coxster groups. He examined what happens when you blow up the 10 nodes of a singular sextic curve, a rational sextic curve in the plane. And he proved that those surfaces have infinite automorphism groups. And in some sense, these examples are modifications of those examples of Cobble, and they're related to work of Dolgachev and Ortland and Harborn and so on, who re-entered this theory of rational surfaces for a third time in the 70s and 80s. But what I want to finish with is just the following sense of mystery. Why are cubics and sextics entering all of these constructions? They're entering because a cubic curve gives rise to a section of the canonical or anti-canonical bundle on the blow-up. This sextic curve gives a section of the square, or the second inverse, rather, of the canonical bundle. Everything is built around using the fact that these curves will be invariant under the automorphism group because they come from canonical curves in the plane. That's why 6 is important. It's why 3 is important. But quite recently, and again, I think this is only possible in the age of computers, Bedford and Kim have found an example that has all the properties of these examples. It has positive entropy. It's lives on a blow-up of just finitely many points. And it has no invariant curves. And they know that these examples of automorphisms of rational surfaces exist by a combination of sort of numerical and mathematical reasoning. But it's a great mystery to know how to construct them. Because, for example, which points do you blow up? These points don't appear to be in any special synthetic configuration. And so I think even looking at these very elementary examples of automorphisms of blowups, or even birational automorphisms of the plane, there's a lot of rich structure that's yet to be understood. Thank you. Yeah.
If it had trace 1 or 2, usually that would just mean you have 3 or 4 isolated fixed points. So why can't you go and do that?
The problem is that what the next step is to figure out what the derivative is of the map at one of these fixed points. And the Atiyah-Bott formula gives you some sort of sum of the eigenvalues over all fixed points, but it wouldn't let you pin down the eigenvalues at any particular one. So it's a restriction of the method. But certainly one could imagine that there are examples with several Zegal disks. I just don't know how to know that they're really there. Bill?
Similarly, I mean, what about Zegal disks around periodic points? Is this, I mean, instead of at fixed points?
Right. So of course, there's very robust methods for showing the existence of Zegal disks, especially if you can figure out exactly what the eigenvalues are at the periodic cycle. So the miracle on the K3 surface was that it was possible to find those eigenvalues on a surface that was not algebraic, for which I had no concrete model of the surface, let alone of the points on it or the endomorphism. But once we get into this realm of rational surfaces, there are actual formulas. And one can certainly compute the condition that a periodic cycle has a Zegal disk now. So there's no reason that they have to be fixed points. I think a much more mysterious question is, if you have one of these Zegal disks, how much of the surface does it comprise? For example, in this case, it's conceivable that this Zegal disk has full measure on the complex surface. We have no idea how big its basin is.
Well, it's not pretty again.